Fantastic. Okay, so now we're going to move on. We're going to go from across the river to down the road, and eventually we'll get out of Cambridge and Boston with our other speakers. But our next speaker, Arvind Satyanarayanan, comes to us from MIT, very far away, but he was on the West Coast before that. He's a new assistant professor in the Department of Electrical Engineering and Computer Science at MIT. And before that, he was a postdoc at Google Brain out in San Francisco. And before that, he was a graduate student at Stanford with our friend Jeff Heer. And he worked also at the University of Washington Interactive Data Visualization Lab. And you will see what we mean by interactive, I'm sure, in his talk, because he says he loves to study interactive data visualization as a petri dish to study questions in user interface toolkit design and human-computer interaction broadly. And I don't think I've ever heard petri dish in the title of a visualization talk, except maybe Felice likes using petri dishes. Felice Frankel here, who some of you may have heard speak last week, is in the second row. So the systems that he's developed have very practical applications, and some of them are actually in use already by Wikipedia and within the Jupyter and Python data science communities. So I'm going to give all of his time to him and just say thank you for coming, Arvind, and I look forward to hearing you talk.
Thank you for that introduction, Alyssa. I'm really excited to be here, and I'm actually now realizing that maybe Petri dish wasn't the best word choice in a room full of actual biologists and astrophysicists and so forth, but hopefully by the end of my talk, you'll get a sense of why I chose to use this. So we seem to be living in this golden age of machine learning, right? This is all around us. And coming from a human-computer interaction and data visualization perspective, I've been heartened to read articles like this from renowned researchers in machine learning. So here is an op-ed that Fei-Fei Li, a professor of computer science, wrote in the New York Times about a year ago. And she writes that she's worried that the enthusiasm for AI is preventing us from reckoning with its looming effects on society. And if we want it to play a positive role, it must be guided by human concerns. And she calls this sort of human-centered AI. And one of her goals of human-centered AI is for this AI to be enhancing and not replacing us. And Stanford recently, under Fei-Fei's direction, has launched a human-centered AI initiative with a whole $1 billion backing it. So that seems like a really good sign of progress. Over at Berkeley, we see something similar. Michael Jordan, sort of a towering figure in machine learning and statistics, wrote that, the revolution hasn't happened yet in artificial intelligence. We have major challenges on our hands in bringing together computers and humans in a way that enhances human life. And really, Michael Jordan is calling for a new branch of engineering that focuses on data from and about humans, informed by the social sciences and humanities. So this is all really exciting, really encouraging. But I want to pause and acknowledge that these aren't necessarily new ideas, right? As often is the case when it comes to research. So back in the 1950s, Licklider wrote this sort of seminal article about man-computer symbiosis. And if we just set aside the unfortunate gendering and take us back to what the 1950s were like in computing, we were talking about mainframes, huge computers that were the size of rooms. The way we interacted with them, so to speak, was with punch cards and batch processing. And yet, back in the 1950s, Licklider wrote that, difficult problems would be easier and faster to solve through an intuitive, guided trial and error procedure, where the computer cooperated and turned up flaws in our reasoning or revealed unexpected turns in a solution. And really, the goal would be to think in interaction with a computer in the same way that you would with a colleague whose competence supplements your own. And this idea was really crystallized in Doug Engelbart's sort of seminal agenda of intelligence augmentation, where he was imagining these situations where our sort of human intuition, our intangible feel for a situation, was partnered with these extremely powerful electronic aids that computers provided us. So with that foundation in place, I want to sort of talk through two sort of threads of research that I've been working on over the past couple of years and draw an analogy between them towards the end. And I want to acknowledge right away that this is not just my work, but work that I've been doing for a lot of years with a fantastic group of people. So let's start with the left-hand side of that diagram and with maybe a more traditional sort of data visualization problem we might have. So let's imagine that we had data about flights. Maybe we have, 250,000 of these flights, and so just a tabular view isn't really going to tell us much. And for each of these flights, we have their source and destination city, the time that they took off, the distance that they flew, as well as their arrival delay. So how might we make sense of this data? Well, a first approach we might take is just to plot them as histograms to get an overall sense of the distribution of our data. And already at this high level, a bunch of interesting trends emerge, right? So down at the bottom here, I can see this sort of weekly repeating pattern where it looks like there are fewer flights on weekends. And one of those top histograms might show us something surprising. Apparently, at least according to this data set, most flights arrive on time. Who would have thought? But that's what the data tells us. So it's great that these visualizations, as Michelle was talking about, are static. We still get a lot of insight from them. But if we introduce a little bit of interactivity, I argue that it amplifies our ability to engage this data in dialogue. So this is a technique called cross-filtering. I drag out a region of interest in one of the histograms, and the bars in all of the others re-aggregate to show me just what is in that little brushed-out region. And so as I drag that region back and forth, some other interesting insights might emerge. So for instance, with the arrival delay, I can maybe see the sort of knock-on effect that's occurring, right? So the longest flights, the flights that experience the longest delays, tend to take off later in the day. And similarly, with arrival delay and distance, I see an interesting effect. Where those flights, if you see when I drag that window all the way to the left-hand side, the flights that seem to get to their destination ahead of time are the ones that have flown the furthest. Now, that's a bit surprising, maybe, and there might be a couple of explanations for that, right? Either airlines are really good at making up time in the air, or if you're a little bit more cynical like me, you're probably thinking they just give themselves a wide margin of error, right, in the times that they quote us on our tickets. So who knows, but at least through this sort of interactive mechanism, we were able to sort of engage this dialogue, engage this data in dialogue, and sort of interactively generate and evaluate hypotheses without having to produce a whole new visualization every single time. So how might we actually do this sort of work? Well, our work has been looking at this notion of declarative specification, or describing what the visualization should look like rather than how they should be computed. And in particular, we've been working on a whole set of different tools that I don't have a whole lot of time to talk about. But why do we care about declarative specification? Well, it allows users to focus on design. So an individual user can more quickly iterate on a particular design, as well as more broadly explore the design space. And the system handles all those underlying execution details. So this makes visualization design accessible to a much larger audience. It also introduces this notion of reuse and portability, so I can write a single visualization specification, and at runtime, reapply it with different input data, or even retarget it so that the same visualization operates on my desktop, my mobile, my tablet device, and so on. And finally, we can build all these systems that I've got in yellow here, these higher-level systems that are able to reason about visualization. So like I said, I don't have time to cover all of these, but I just want to look at this system called Vega Lite. And here is what a visualization in Vega Lite looks like. It actually produces this much more complicated visualization in that lower-level language called Vega. But in Vega Lite, we're just talking about very high-level details of a visualization. Things like on the X dimension, we want to plot horsepower, on the Y dimension, miles per gallon. And the reason we're able to only operate at this high level is because we're omitting a lot of low-level details, like what scale functions we need, what axes and legends. And instead, Vega Lite is filling those in with sensible defaults, including perceptually effective color scales and so forth. But as a user, I might know better, and I might choose to override them. So I can just do that in line right away. So here I'm specifying an alternate color scheme, not making any claims that this is a better color scheme, but at least we have that ability to do so in the language. Now, as I mentioned, interactivity is really a key part of visualization. And how do we do interactivity in Vega Lite? Well, we introduce these building blocks called selections that we define, and then we can use as part of these simple if-then-else statements. So here we've got a selection called pick, and we say if a point lies in picked, well, then we're going to color it based on a particular data value. And if it's not in that selection, we leave it in gray. And so these selection types are much like the regular visual encoding that we see. We're not specifying any low-level details, like what events are we listing for, is it mouse clicks or hovers. The compiler figures all of that out for us. But again, as the user, I might know better, and so I can go ahead and override those defaults in place. So now, instead of driving that selection with a click, I'm saying it's on mouse hover, and so as I move my mouse pointer around, those points are getting highlighted rather than on click. But if I had to continuously provide these overrides, well, I've not really done a very good job of designing this language if the user continuously sort of has to, circumvent the system. And so besides these manual overrides, we also have this notion of a selection transformation. So just like we have data that we might transform, we might filter it, we might sort it, we might aggregate it, so too we think about interaction. How might we transform the semantics of an interaction technique? So right here we have a single selection that's saying, when I click a point, select it and highlight it. But I might want to instead say, well, select all the points that share the same number of cylinders, a particular data field. And so I just specify that in line, and now my selection logic has changed. My interaction logic has changed. When I click a particular point, all the other points that share the same number of cylinders are highlighted as well. Now, this manipulation is all happening directly on the visualization, and so you see those 3 large groups pop out, roughly corresponding to about 8-cylinder cars, 6-cylinder cars, and 4-cylinder cars. But I don't necessarily have a sense of, am I being exhaustive in my interaction? Am I getting all the data has to tell me? And so an alternate way I might choose to drive this interaction are through dynamic query widgets, or range sliders in particular. So I, again, introduce that through a selection transformation, and I can grab this range slider and just move it back and forth to now give me a much more exhaustive sense of the sort of cylinder space. And because Vega Lite makes generating these visualizations so much easier, this language is so concise, I can rapidly generate and evaluate these hypotheses just by adding a few lines of code to my visualization. So now I've gone from not looking at only the cylinders of the particular cars, but also looking at how these cylinders change over years. And maybe a hopeful note here, as I get to the more recent years, those points seem to move up the scatter plot, telling me that these cars look like they're getting at least a little bit more efficient. So with Vega Lite, we're able to produce a whole wide variety of visualizations. So here is a scatter plot matrix where I'm able to not only pan and zoom the scatter plots, but also brush within them. And each of those scatter plots are kept in coordination with each other. I can do this thing called an overview plus detail, where I brush in the top, and I see those points at a higher resolution in the bottom plot. I can do interactive renormalization. So here is a line chart of stock series, stock prices. And as I move my mouse cursor back and forth, I'm re-indexing, re-normalizing all those points so that I get a sense of what the percentage increase or decrease would have been had I invested in those stocks at that given date. And finally, here is this sort of a variant of that interactive example I started with, cross-filtering, except this time we're highlighting the bars instead of having their heights move up and down. And what we're talking about in all of these visualizations are 5 to 10 to 20 lines of code, which is sort of an order of magnitude or 2 improvement over the prior state of the art, which is this toolkit called D3. And Vega Lite has this other really interesting property, which is that each of those little additions that we make to the language actually carry semantic meaning to them. And so I can build these really interesting graphs out of the design space of Vega Lite visualizations, where each of these represent an atomic step, an introduction of just a single property in a Vega Lite specification. So this all feels a little bit academic, right? Why do I care about enumerating the design space? Well, what it allows us to do is build these higher level systems that reason about visualization and data analysis. So an example system that my colleagues have built is called Voyager, which allows us to automatically recommend visualizations for us based on perceptual effectiveness and data distributions and things like that. My lab has also been working on a system called Lyra, where the idea is, what would it look like to do visualization design in a graphical user interface? So what if I started dragging and dropping fields instead of writing sort of textual code to get me a visualization? And all of this is driven by Vega and Vega Lite underneath the hood. Now, as Alyssa mentioned, a lot of this software has seen adoption in industry. So we've been working with folks at Wikimedia and Jupyter and Google. We've got 800 pages on English Wikipedia using Vega visualizations. Folks in the community have said it's the sort of one-to-one mapping between their thinking, the code they write, the visualization that gets produced. That's their favorite thing about using these libraries. And the folks on the Jupyter side, the Altair team, consider Vega and Vega Lite to be our best existing candidates for a principled visualization language. All right, so that's that first thread of research. And now I want to swap to the second. So here are two dogs. How many of us think that these are the same breed of dog? And how many of us think that they're two different breeds? Oh, wow, so a very small number of people think that they're actually two different breeds. So it turns out, well, I don't know if I'm using breed correctly or not, but it turns out there are different kinds of dogs, Labrador Retriever, Golden Retriever. When I looked on Google Images for this, I had to be like doubly sure I was making this slide correctly, because I thought they were the same kind of dog. Turns out humans aren't really good at making these sort of subtle distinctions, but machine learning models have gotten really, really good at identifying, in particular, different kinds of dogs and cats. Why is this? So this is a state-of-the-art model from a few years ago now. And the basic idea is you feed in an image of something, and out pops different classifications with an associated probability of how likely it thinks it is. That's right. So tennis ball is up here, and there's an interesting reason why. I don't know if I've got it in my slides, but we'll see. So out pops these labels and associated probabilities. And basically, the magic is happening in these things called the hidden layers. So each of these hidden layers is basically, you can think of it as computing this matrix of x and y positions, as well as these things along the z-axis called channels. And I don't want to spend too much time digging into what each of these particular things are, but let's just consider what is happening along each of those columns, so at each of the spatial locations on a particular image. So you might say, great, we could build a little interface to just tell us what is happening as I move my mouse pointer along each of those particular positions. Well, that's what's happening. 0, 0, 45.8, 32.3, so on and so forth. Doesn't mean a whole lot to me. I don't know if it means a whole lot to anyone here. Turns out there's this technique called feature visualization that several of my collaborators have worked on. And the idea is that if you treat it as an optimization problem, you could start with an image of just random noise, feed it into the neural network, and have it optimize some particular objective. So in this case, we're saying, perturb the image until you maximally activate some particular neuron in this neural net. What this essentially tells us is that this is what that neuron that you optimized for is kind of seeing or looking for in the image through this process. So if we take this idea of feature visualization and sort of apply it to each of our positions in the image, we get something like this. As I move it around, well, now I've transformed those numbers that didn't have much meaning, into these iconic representations of dog snouts and floppy ears and bits of grass. And we call these semantic dictionaries, right? Because now we're able to articulate these neurons in sort of human understandable terms, with human understandable words. Here's another example, a man wearing sunglasses, and you can see, oh yeah, there's like a weird looking eye detector there, kind of like an ape face detector. There's one down here with his bow ties and like his lapel. Or even this one with flowers in a vase, right? We've got flower detectors here. We've got like vase detectors and even like little angular detectors with these lemons and things like that. And even though we've done this transformation from those abstract mathematical notations to these iconic representations, underneath the hood, these are still mathematical constructs. And so I could do some basic math with them, like add them together. And so now I've not only got the little individual neurons that are firing at these particular positions, but I can sum them up together and say, at each position, this is what the neural network is seeing. And right now, I've kind of kept this interactive so that you're seeing it as I move around. But sometimes static visualizations are the better approach. And so we've, instead of forcing it to be an interactive function, we've plotted all of those in the same space. And now you've got this grid of activations for a particular layer. And what's interesting is we see a progression in abstraction across these layers. So right at the start of the neural net, it seems to be detecting these edges. You move one step up, and it starts to look at geometries. Another step up, it's starting to understand parts of objects. And then finally, sort of right at the end, it's really made up its mind about what it's seeing. And if you put them sort of side by side, you see this sort of progression from really low-level properties of the image all the way to high-level properties. And so we explored a bunch of these design spaces in this article on the Distill Journal. But what I wanted to do in my talk was take a slightly different angle, which is to say that this gives us an alternate representation into what makes an image. For the longest time in computer graphics, we've only really sort of thought about the red, green, and blue color channels. And now, through neural networks, we've got a representation of images that are talking about edges and geometries and parts of objects. Well, what can we do with that? Can we build a sort of semantic painting application that allows us to paint not just with red, green, and blue, but with these parts of objects? Turns out we can. So colleagues at MIT, David Bao and al., have actually built such an application. So you can go in with this GAN dissection program and add trees and remove grass and add domes and things like that. So this is a fantastic sort of view into what is possible that they've been working on. But there's still so much left to explore, right? This is still looking at whole trees, whole grass, not getting at the edges and the parts of objects that we saw the neural network was detecting. And so this is where I try and draw an analogy, where all of these higher level systems that we want to explore, these direct manipulation, visualization recommendation, the semantic painting, are based on these layered abstraction models that we're building that are domain specific. And on the left-hand side, we've arrived at them through tons and tons of PhDs. And on the right-hand side, through tons and tons of data that we ran through a neural network. And so what my group is increasingly thinking about is what this intersection looks like. How do not just neural networks, but domain experts and automated systems collaborate around these domain-specific abstractions? And in particular, when I say domain-specific abstractions, I talk about things that expose domain semantics. So in Vega Light, we were talking about the X and Y dimensions, color, scales, things like that. And they're layered because we want folks to be using a representation that makes the most amount of sense for them at the point in time they need it, right? We don't want you to use something really low level if what you want is something really rapid and concise. And we also really care about this idea of balancing automation and user control. So we know that people exhibit a lot of cognitive biases, right? We tend to fixate on our hypotheses really on. We're not good at large-scale repetitive tasks. And yet, if you entirely automate the human out of the loop, well, we risk de-skilling folks. We risk loss of attention. We risk loss of expertise and accuracy. And so how might we better balance between these two worlds? So looking ahead, some of the things that my group is working on is, first of all, just advancing visualization. So can we run things like empirical studies, which I'm sure Danielle will talk about a little bit on the visual side, but we're focusing on the interaction side. Can we think about what makes one particular interaction technique more effective than another? On the side of automated systems, I showed you that Lyra system really briefly. Lyra just looks at static visualization. How do you design interactivity in this sort of direct manipulation by demonstration kind of approach? What would a visualization spell checker or linter look like? How would it identify poor design choices and suggest improvements? Is this perhaps a way that we can also start to build visual literacy in folks? And finally, can we make sure that building these domain-specific abstractions doesn't require PhDs? How might we generalize our approach to other domains like data science more broadly, personal information management, and like I said, lower the threshold for working with these? And so just to wrap up, why do I consider visualization a petri dish for all of this work? Well, we saw with Michelle's work how visualization applies so broadly to a number of disciplines. Working just in computer science, I found exactly the same thing. My work has touched everything from machine learning through databases, through programming languages to human-computer interaction. And so I found that visualization is this really nice medium that places a bunch of constraints on us. We have a much smaller design space than some of these other disciplines. And yet that design space is sufficiently expressive, sufficiently interesting that we're still able to answer some of these really deep questions about intelligence augmentation. So, like I said, a lot of this work was done with some fantastic collaborators, but I'm particularly excited to continue it with my fairly new group over at MIT and my students there. So, thank you very much.
That was wonderful. We're going to take just one or two questions now, and we'll ask more questions during the panel. So, and then we're going to have a short break after this. So we don't want you to lose the break entirely. So I'll leave it to you to take two.
Hi.
Terrific.
Thank you.
I deal with images. And for years, I've been asking my computer science friends if they could come up with a way of giving meaning to the layers.
Yeah.
In other words, your work is, at this point, seems to be about structure and form and identifying those compositions. But what about the meanings of the layers? Can that ever happen without a human being?
So could the system sort of automatically, interesting. So it's funny you should raise this because I think one of my students is actually working on a variant of this problem, which is, these domain-specific representations, the domain that they're specific to are visualization construction, and not a particular application domain, if you will. And so one of my students is actually now thinking about, well, can we encode, gender bias in natural language as some sort of domain-specific representation? What might that look like? That's a really broad question, so we're in the process of figuring out how we take our first step towards answering that. But once you have, it always goes back to these domain-specific representations I found, because without them, your computer systems just don't know what they're talking about, right? They're just looking at sort of a generic piece of programming code in JavaScript and C++ or something like that. And so through this approach, we're actually able to bring in semantics that humans understand, but now give computers leverage over. All right. Great, thank you.